This call is now being recorded.
Hello, is my screen visible to all?
Yes, it's visible. Um, okay, so our project topic is detection of diabetic retinopathy using image processing and machine learning. My project group members are Yash Joshi and Aniruddha Tupe, and our guide is Jayadevan ma'am. So these are the contents of our PPT. So introduction of the disease. So diabetic retinopathy is an eye condition that can cause vision loss and blindness in people who have diabetes, and it affects the blood vessels in retina. And the disease is mainly divided in four stages, uh, as it is given: mild non-proliferative diabetic retinopathy, moderate NPDR, severe NPDR, and proliferative diabetic retinopathy. Mm. So the motivation behind this topic was that many patients, diabetic patients, have diabetic retinopathy disease, and so as the treatment, uh, so if the disease is detected early, it will be easy to cure, and it will prevent people from the blindness. So our problem statement is diabetic retinopathy is the leading cause of blindness among aged adults, and if it is detected early, it can be cured. But to review the fundus images, provide diagnosis, highly trained ophthalmologists are required. So the aim and objective of our project are: the aim is to develop a solution for diabetic retinopathy to provide easy to use interface for this disease, and the solution should be portable so that it can be used on any smartphone. The objectives of our project are build an easy mobile application to detect DR and use image processing technique to remove unwanted noise in the image. Next, now Aniruddha will continue.
Yes, thank you, Snehal. The literature survey we have, the literature survey we have done for this project was mainly divided into three topics. First, diabetic retinopathy screening techniques using fundus images. Second is optical coherence tomography, and third is scanning laser ophthalmoscopy. Next slide, please. Yeah. So the first paper was by Sonali. It proposed a method for enhancing retinal fundus images using CLAHE, which is contrast limited histogram equalization. In this method, though DR is not detected, the fundus images are made more suitable for its detection by denoising and enhancing its contrast. Second paper is by Sarvinda, wherein they classified DR stages by extracting features using histogram of oriented gradients and classified them using support vector machine. Next slide, please. The third paper that we reviewed was by Kalpiappan and others. It proposed a method which focused on detecting exudates in fundus images which were clicked using a mobile phone. The fourth paper that we reviewed was by Long and others. It came up with a technique for detecting hard exudates using dynamic thresholding, followed by classification using support vector machine. Next slide, please. The fifth paper was by Ghazal and others. It used optical coherence tomography for detecting non-proliferative DR using CNN. And the final paper was by Hagos and Kant. It used a method of transfer learning for detecting DR on a small data set. Based on this literature survey, we proposed our own methodology. In our methodology, dataset is of the dataset used is Aptos 2019 dataset. It is split into training and testing datasets. Then pre-processing is done using CLAE, which is contrast limited adaptive histogram equalization. The trained images are then passed to an inception V3 network, which trains on the images, and then evaluation is performed. And training is done using transfer learning from ImageNet training weights with the Inception V3 model. So from
Okay.
here, Yash will continue.
So as Anirudh mentioned that we will use the inception v3 model. So for that, the first step that we required was to get a data set. So we are using the Aptos 2019 Kaggle competition data set. So this data set basically has five classes, but those were unbalanced. There were a lot of images of class 0 and less number of images for the other classes. So we first converted that five class dataset into two class dataset, and then the dataset was split into training and validation in the ratio 80 to 20. Uh, these images then undergo pre-processing using class A, and then after this they are fed to the inception v3 model to begin the training. After the training is complete, by using efficiency measures, the model finds its best state and freezes at that point, and to gain higher accuracy. And after it's frozen, it generates a .h5 file. Then this .h5 file is fed to TensorFlow.js, uh, so uh, so that we can use it in our application. And after it is fed to TensorFlow.js, it generates a JSON file and its corresponding weights in bin files, so that we can import it into our front end project. So, as I mentioned earlier, the data set is provided by Arvind Eye Hospital, and initially you can see the graph that the classes were not equal for the five, but once we combine it into just positive and negative, that is no DR and DR, so it becomes balanced, which is good for our training. So talking about Inception V3, so it is a highly uh, like a widely used image recognition model, and it attains greater than 78% accuracy on ImageNet dataset. So our main aim was to use transfer learning, wherein some of the initial layers of the Inception V3 like extract features from the images, and then uh, we add our dense layers to use it to convert into a two class output. So the main feature of Inception V3 is that it burns less power, and it focuses on going wider instead of deeper. Like most of the neural networks focus on going deeper to find the features, but Inception V3 focuses on going wider, which makes it, which makes it efficient as well as economical. So. So basically, our architecture starts with an input of 299 by 299 by 3, and it is then followed by some convolutional layers, and then as we can see over here, there is a inception A layer. So as I mentioned earlier, it focuses on going wider instead of deeper. So the inception A layer is the best example of this. So basically, as you can see over here, the inception A layer has uh, like parallel convolutional operations, and then they are concurrented at the ender. So this is the the basic definition of going wider instead of deeper. And then similarly, there are reduction A, inception B, and inception C blocks, and which is later followed by dense layer, which uses softmax classifier. So these are the wider architecture of Inception V3. So this is the Python implementation. So as we are using transfer learning, we are using the weights of Inception V3 trained on ImageNet dataset, and then after that, so here we can see we add our own dense layer. As by default, the Inception V3 outputs into 1,000 class output, but we require only two class output. So the model is modified, and then the model is saved. So after the training, we can see that the model stops itself after 12 epochs, as it is a best case scenario, and after training, we found that the accuracy was greater than 98%, and the loss was less than 0.05%. Uh, so about Clahe, Anirudh.
Yeah, 1 second, the slide is loading. Yeah. So thank you, Yash. As Yash mentioned, for pre-processing, we have used CLAHE. CLAHE is basically contrast limited adaptive histogram equalization, wherein it limits the application by clipping the histogram at a predefined value. This limits the slope of CDF and therefore of the transformation function. As you can see, the original image on the left side doesn't give much features, whereas the contrast enhanced Clahe image gives much more details in the image. Basically, the Clahe increases the contrast and improves the image by removing noise, thus making it fit for training purpose.
So the tools that we have used uh, for the complete development, so basic program language that was used to train the model was Python, and we are using TensorFlow with Keras at a backend. And since our laptops are not graphically intensive, we are using Google Colab's GPU to train at a higher rate and get better efficiencies. So this is the part of the training, and then for development of application which a user can easily use, we are using Node.js, Angular, Express.js, and MongoDB as a database. Express is used to develop APIs, and so for the app to run, we require just that it should support Chrome with greater than 47 version and good internet connectivity. So for the system requirements, we plan to go with PWA, which are also known as progressive web apps, which basically are lightweight applications that use engine of our browser, our mobile browser, to process the web pages, and it basically is a lightweight application, and we don't need to we don't need our mobiles to have lot of compatibilities and updates all the time. And so basically that is it. Snail.
So we have participated in an event hosted by MIT, and we presented our idea there. This is our participation certificate. Um we have published a paper, and a paper is accepted, and they sent us some review, and we made changes accordingly. Uh, this is a certificate from the conference where we have presented our paper. Okay, yes.
So the summary is we have done literature survey where we have found out that Clahe is one of the best techniques used to enhance the fundus images, and which denoises and enhances the fundus images, and other imaging techniques such as OCT uh, were also studied, but among those, fundus images are most widely used, as well as the cheapest to capture, and Hagos and Kant used transfer learning method. So we are trying to achieve. We are trying to modify their model. So we are also using transfer learning, but our model is Inception V3, and with Clahe as a pre-processing. So these are the references. So I'll proceed with the demo. Okay, so So basic is my screen visible now? Are the two web pages visible?
Yes, yes.
So basically, what does a PWA mean? As I told before, a PWA is nothing but something that is app that runs on the engine of a browser. So, like we can see over here, the it is given here Pixel X2. So this is kind of how it will look on a mobile display on both the sides. Uh, so basically, we have made a Mongo database which has a list of patients and their corresponding history and a list of doctors, and the doctors can access these patients' data. So there are a lot of validations added, as you can see. It says that front end validations are there. Also, if there is no user present, and if we log in, so here we can say it shows that the user is not present, and so this is a part of feedback mechanism. And if we log in with the right user, we are forwarded to the user's dashboard. So in the user dashboard, the user can basically add an image. So so we have used Aptos dataset to train, but now I will be testing on I IDRID dataset. So as you can see the CSV file, it shows that the image name as well as the level of DR of that image. So so we can upload a file, and so this is the images that we can see in this corresponding to this CSV file. So if we select one of the file and then we click pre-process and predict, so it will load for some time. uh, so here you can see we uploaded 18th image, so it shows that it has DR. uh, and yes. Okay, so the diagnosis came out wrong, but with a lower confidence. Let's try. So basically, this is the UI which shows that which shows the pre-processed image on the right side, like after Lahe is applied on the image, and then we can see. So like this is a best example to show why we need a doctor side. So for example, if the model fails as it is not perfect, the patient can save this result. So after the patient saves this result, we get a small pop-up saying that the result has been saved. And once we go to the history, we can see over here that the image that we uploaded is added to the patient's history. So on the other hand, a doctor can access this patient data. Okay, so the doctor has options to view patient, and then he can click on the patient names. So I had logged in with Anirudh's login credentials. So here we can see the last image that is shown. So the doctor can zoom into the image, and then he can see this image like and give provide his own diagnosis. For example, now we know that this is a wrong prediction, so we can give that wrong prediction, and then patient has DR, and he can submit it. So it says like it is submitted. Once again we go back to the patient dashboard and we go into the history, then we can see that after the doctor has given his comment, so even if sometimes the model fails, the doctors are there to provide support to like say when the model fails or what is wrong with the prediction. So yeah, these are the basic use cases of our app.